This is CS1101, lecture 4.1. Today we're going to be looking at the difference between chars and strings and discussing some of the details of chars, as well as discussing the effects of short circuit evaluation on conditional statements. So we've introduced a lot of relational operators such as less than or equals or not equals, greater than or equal to, those sort of operators. It's important to understand that these relational operators are only intended to behave correctly on primitive values, or they are only claimed to behave correctly on primitive values, so primitive data types. So this is the reason that string has a built-in method for comparing that we discussed previously. Strings are not primitive types. Strings are actually objects which are made from primitive types. Specifically, strings are made from chars. So a string is not a primitive type, and therefore the equals operator is not going to behave in all situations. It'll return a value, an expression which uses equals to compare two strings will return a value, a Boolean value. However, it may return false even if the content of the string variables is precisely the same. So for this reason, it's always important to use the .equals method that we've discussed in the previous lecture. But what about case sensitivity though? So how does .equals check case sensitivity? Is uppercase T, uppercase N the same thing as uppercase T, lowercase n when using the .equals method of a string object? To answer this, reference the table below. The equals method is going to return true if the strings contain precisely the same characters. This statement should be understood literally. What I mean by that is the char value which represents a character is different for the character which is lowercase and that same character which is uppercase. So they are technically two different characters, and there are two different values in the char encoding which represent those characters. So therefore, yes, the equals method built into the string object is case sensitive. If you want to compare two strings while ignoring case, there's a method for that as well. And there's also a method to check to see if the beginning portion of a string matches some parameter that you wish to pass. So, in the case where we wanted to see if the word conditions started with the prefix con, then we could have the string conditions stored in a string variable, and then call that variable, let's say, word, and we could say word dot starts with, and then pass a string which contained con as the operand, and it would tell us whether or not the string conditions begins with con. Obviously it does. This would return true. Similar thing with ends with. We can tell if a string ends with a particular string, or if anywhere in a given string variable a string occurs. So, in the case of the word several, perhaps we want to know if at any point in the word several the string er occurs. So yes, it does, right? So we could store several into a string called word, and we could say word dot contains and pass it the string er, the string literal er, and it would tell us whether or not several contained the substring er. So here are some examples of the uses of these various methods for returning a Boolean value and testing a string. Now notice that we are making an assumption about the existence of a string variable called title, full name, last name, name. So we haven't instantiated those, we haven't declared them, and we haven't given them a value, so just assume that happened previously. So to find out whether or not someone's title ends with PhD, we have a string variable which was declared somewhere up in the program up here, we assume, and it's called title, and it was assigned some string value. And now we want to know if that string value which it was assigned ends with PhD. So we can use title.ends with PhD. This will return a Boolean true or false based on if the string stored in title ends in PhD. If it does, it will return true, in which case this Boolean expression will evaluate to true, and we will execute the statements within the curly braces following the if statement. Same thing going on here. We've got some string variable called full name that was declared and assigned a value previously. And we want to know if it starts with queen, in which case we're going to say greetings, Your Majesty. Okay, we're going to look at last name. So again, we've got a string variable that was, we assume, declared previously and instantiated and assigned a value. So we are going to test whether or not the string last name is equal to Sean Mendez while ignoring the case. So we're wanting to check and see if the letters are the same, but we don't care about case. And lastly, this is a slightly more complex situation. So we have a string variable, a string object called name, and we want to convert name to all lowercase. So understand what's happening here. This is a string object called name, and we're accessing a method which is a part of the string class called toLowercase. And this method will return a string object which is the string stored in name but with all lowercase characters. So this is replaced by a string which is the same as name except it has all lowercase characters. So now this is a new string, and we are accessing the contains method of this new string, and we are checking to see if this new string contains the characters JR period in that order. So the string junior, in which case it will return a Boolean value of true or false, and this will ultimately evaluate to a Boolean expression. And if it's true, we will print out, you are named after your father. Consider why it was necessary to first convert the string to lowercase and then check if the string contained junior. The reason was we couldn't use the ignore case because we didn't want to check if the entire string was equal. We wanted to find out if the string contained a substring anywhere within it. And there's not built in a method which checks for a string containing another string and ignores case. So to be able to do this, we had to convert to all lowercase and then check for containing the lowercase version of junior. So this is the list of commonly used string methods. toLowercase, we've looked at this already in the previous slide. It's going to return a new string which has the exact same characters as the previous string. However, each of the characters which was uppercase in the original string will be lowercase in the returned string. The method substring is going to extract a portion of the string contained in a variable. So remember, if we have a string, let's say we've got a variable called name, and this is a string type variable, so the data type of this variable is string, and we want to ignore the first 5 characters and keep the rest of this string. So we could say name dot substring, and then as an argument we said we wanted to ignore the first 5 characters. So the index begins at 0, so the very first character has an index of 0. The second character has an index of 1. Third would have an index of 2. The fourth character would have an index of 3. And the fifth character would have an index of 4. So therefore, we want to get the substring which starts at 5, and this will ignore the first five characters and return all characters after that point. Substring has a variant which allows you to define the start and end. So let's say we didn't want to have just a start point and get everything after that. We wanted to be able to extract something from the middle. Well, then we would define both the start and end. So we could say name dot substring, and then we're going to start at character at the character with the index 5, and we're going to go to the character with the index 10. Notice it does not include character 10. So technically this would return characters 5, 6, 7, 8, and 9. A lot of times, if you're reading in a file, then you might wind up with having leading or trailing white space, so a bunch of spaces at the beginning of a string. Well, the trim method provides an easy way to return a string having removed all leading and trailing white space. Last index of is a way to find out what the last index of a string is. So in the substring method, we said we wanted to get all of the characters between index 5 and 10. Well, what if there wasn't an index 10? What if this word is only 10 characters long? That means the last index is going to be 9. So therefore, we potentially may have tried to access something that didn't exist, in which case our compiler would throw an error, or we would have a runtime error, just depending on if it was hard coded or if it was actually if it was variable and happened while we were running. So a way to check that is to verify that the last index of the string is greater than the index we intend to access. So we also have a method called compare to. Compare to is a method which is used to find the lexicographic ordering of two strings. Lexicographic ordering can be understood to be alphabetic ordering, but this method also works with numbers, and it also considers the case. So you can look up lexicographic ordering on your own if you want to know more about that. But essentially what happens is if the string A string is to be considered first in lexicographic ordering, then this will return a negative integer. However, if the string which is contained in the string variable is considered lexicographically equivalent to A string, then this will return 0. However, if A string follows the string contained in the variable, then this would return a positive integer. There's also a method to concatenate a string with the string stored in the variable and return a new string, which is the two concatenated together. We've seen another way to do that already, just using the plus operator. And then finally there's the equals, which we've talked about, which is a test to see if two strings contain the same characters. We've mentioned that there's a primitive type called char already. So then, if a string is just a bunch of characters, is char a primitive or is an object? Because we said strings are objects, not primitives. But strings are just a bunch of characters. So what's going on here? We alluded to this already, we mentioned it, but let's make it more clear. Char is a primitive type, but it only can contain a single character. So you can't have a whole word. You can only have one character. So for instance, this would be a char literal. So this is how you would type a char value into the program. And so all that char contains is the letter A, the lowercase letter A. There's no way you can form words out of this. So string is a data type which is used to house multiple chars. So each individual character inside of a string is stored as a char value. But the nice thing about a string type is that it allows us to have multiple chars stored in one variable. It would be cumbersome if we needed to have a variable for every letter in a word. That would get old and it would get annoying. So it's much easier to have a data type called string, which contains multiple characters, and it does that heavy lifting for us. And under the hood, each individual character in that string is a char value. Notice even in char values here, we have escape sequences. So to be able to represent a new line character, we would still use the /n. And to be able to represent a single quote in a char, we would do / single quote. And as I mentioned, to type a char literal into a Java program, you surround it with single quotes. Strings are surrounded with double quotes. Char values are surrounded with single quotes. Sometimes in programs it's necessary to deal with chars, and typically in those situations we'll wind up dealing with sort of a hybrid. We'll wind up dealing with some chars and some strings. So a little bit about how to manipulate chars and strings. So first of all, we can use the plus operator on chars and strings just like we use the plus operator on ints and strings or toStrings. So the plus operator will work in this situation as well when we are doing a char and a string. So when we used an integer and a string, we said an integer plus a string or a string plus an integer will result in a string. Just the same, a char plus a string equals a string. So the result of this addition would be a string. So we would wind up with p dot ditty. It's also perfectly fine to have variable decisions, parameters, and returns of type char. So what I'm saying here is that we can have a variable called letter, which is declared of type char, and we set the value of the variable letter to s. And then we can, as with any primitive type, we can use the is equal to operator to yield a Boolean expression, and then we can pass this variable as a parameter to the print line statement. So we can work with chars just as easily as we can work with integers and other primitive types. So let's say that we wanted to access a specific character in a string. So we have the word cookie, and we have it stored in a string type variable called food. The way to get the char from a string is to use the char at method. So to return the char, which is stored in the first position of this string, we would say food, because that's the variable, food dot char at, and then we give the parameter 0 because we want the character which is in the index 0 position. And remember, we start counting from 0. So 0, 1, 2, 3, 4, 5. So C has the index 0. So now this method returns the char value C, which is then assigned to the variable first letter, which is a char type variable. Then we have a print line statement which will add the first letter with a string, and will also add the food. So this is an expression. We are well versed at this point in evaluating expressions. We understand the precedence of operators. In this situation, we have two operators of equal precedence, so we work from left to right. So the first letter is a char, and it is being added with a string literal. So char plus string results in string. So we now have C space is for, and that is stored in a string, and then we're adding that with another string. So string plus string equals string, C is for cookie. And then we will have another print line statement that displays the string literal, that's good enough for me. So char is a data type which is used to store characters. But for characters to be represented in a computer, they have to be encoded in some way, because computers are only able to store fundamentally ones and zeros, so therefore combinations of ones and zeros, and we understand that that makes up a binary number system. So all we can store in computers is binary numbers. So then we have to have some way of encoding a char as a binary number. When I say a char, I mean a character. So we have to have some way of encoding, for instance, the letter A as a binary number. So the solution for that is used is called ASCII encoding. So ASCII is just a numerical encoding which encodes letters as numbers. And that's how they're stored in the memory of the computer. So when a char has the value capital A, what's actually stored in the computer is the number 65. Capital B is 66. A space is 32. Lowercase a is 97. Lowercase b is 98. And the character star would be stored as the value 42. So interestingly, these numbers are integers, and a char can be interpreted as an integer. So think of it this way. We have some memory location in a computer, and we want to store the letter uppercase A. So what happens is our computer, or our Java program, will write down in that memory location the number 65. Now, anytime that we make use of that char, Java knows to interpret the number 65 as the letter A because of the ASCII encoding. However, it's still written down as the number 65. So if we wanted to, we could actually use the number 65 as an integer. There will be situations in the future where you want to make use of the number which is stored in memory to represent the character of a char, so the ASCII value which is written in memory. And it's very easy to do that since fundamentally in memory they're both stored as integers. So in Java, if you were to type in as an expression the character literal A plus the integer literal 7, the result would be 104. The reason is because in memory, A is stored as the integer 97. So 97 plus the integer 7 equals 104. So as a rule, if we have a char plus an integer, the result is an integer. Now, pay attention that this is different than if we did a string plus an integer. String plus integer results in string. Char plus integer results in integer. So if we wanted to instead get a result which was of type char when we did A plus 7, we would have to do a typecast. So think about what's actually happening here. Let's say that someone told you a riddle and they said the correct solution to this puzzle is the character 7 after A. So, in your head you could say, okay, well, A, B, C, D, and kind of count it off and figure out which character that was. But let's say we wanted to write a really simple program in Java to solve that very simple riddle. Well, we could do char literal A plus integer literal 7, and then cast this value, which we already know the value is 104, we can cast the value into a char. So what we're telling Java to do is interpret this integer as an ASCII value, and it will give us the ASCII value which corresponds with 104. In this case, H is represented by the ASCII value 104, lowercase h. So what we have done is we wrote an expression which is char plus integer, which results in an integer, and then we told Java that we want to typecast it as a char. So Java interpreted 104 as an ASCII encoding and gave us the letter represented by, or the character represented by 104. So notice the bottom style example. Since a char is actually fundamentally written down as an integer, we could have a char variable called ch. So this is a variable called ch with the data type char, and it contains some character, and we want to know if that character is an A. Well, there's two ways we could go about this. We could test to see if the variable ch is equal to the number 97, the integer literal 97. This would test to see if ch contained the character A or not. However, that's not very readable because I don't have the ASCII table memorized. I don't have the full ASCII encoding memorized. So if someone had written in code ch is equal to 97, I don't know what they're intending to accomplish. However, if someone has written in code ch is equal to the char literal A, I know exactly what they're trying to accomplish. They're testing to see if this character is an A. So this is much better style because it is readable and it is transparent. Again, just because something works doesn't mean that it's the right way to go about it or a good way to go about it. Hopefully strings and chars, as well as the rest of the data types we've talked about so far, are starting to make sense. If you need more practice on understanding these, refer to the zyBooks material, to the zybook activities, and also the Regis textbook. So now we're going to turn our attention to looking at how some logical operators execute. In Java specifically, some logical operators perform what is known as short-circuit evaluation. To understand what short-circuit evaluation is, think about using a logical AND operator. So a logical AND operator is shown here in our truth table. So P and Q, P logical AND Q. So consider the following situation. We have the binary expression P and, this is a logical AND Q. But we're going to say that P is equal to false. So we're just going to set that as a given. That's something we're going to say about this particular situation. So now let's rewrite this. So false and Q. What will this new formula evaluate to? What will this binary expression, false and Q, evaluate to? Well, how could we know, right? We don't know the value of Q, so we only know the value of P. Is there any way we can possibly figure out what this binary expression is going to evaluate to? Well, to answer that, let's look back at our truth table. So we said that P is going to have a value of false. So only these last two entries in the table are relevant, because we know that P is not going to have a value of true. So we're definitely in one of these two bottom rows. Now we don't know which, because we don't know if Q is true or if Q is false. But notice in the P and Q column, okay, there are only two values, we said, possible for Q, true and false. But what is interesting is, regardless of the value of Q, whether it's true or false, P and Q in both situations is false. So this is called short-circuiting. The reason that this is possible to do is because anytime a value in an AND statement is false, the entire AND statement is false. Notice, at any point that either P or Q is false, AND is false as well. So if any value in a logical AND operation is false, then the entire result of the expression must be false. So for this reason, when we are evaluating logical AND operations, we evaluate the very first operand and see if it evaluates to true or false. If it evaluates to false, then we don't even move on to the rest of it, because we know that the entire Boolean expression is going to evaluate to false. We can do something very similar for OR. Notice that for an OR operation, if we have a true for P, we don't care what Q is. Regardless of what Q is, P or Q will be true. So Q has no effect on the result of a logical OR operation if P is true. So two rules here. The first is that if any operand in an OR statement is true, so let's modify this. If any operand involved in a logical OR operation is true, then the entire expression is true. If any operand associated with a logical AND is false, then the entire expression is false. So for this reason, we execute logical AND from left to right, and we execute one expression at a time, evaluating to see if it is true or false. So when we're executing an AND operation, if we encounter any value that is false, we stop. We don't even look at the rest of the operands. This allows for the runtime to execute much faster, because it doesn't have to go through and check the other operand in this situation, Q. So consider a situation here where we have the following example. We have this conditional statement: if number, which is some variable, if number is not equal to 0, and, logical AND, some other variable called sum, divided by number is greater than 5, then we're going to do some operation. We don't know exactly what they're accomplishing here or what they're attempting to do, but notice this. What happens if number has the value 0? What happens if the variable number has the value 0? Well, we said that logical AND will attempt to do a lazy evaluation or a short circuit evaluation. So since it's an AND operation, if any operand in the AND operation is false, then the entire AND operation will immediately be short-circuited to false without considering any of the other operands. So, on the left, we say number is not equal to 0. Well, actually number is equal to 0, so this will yield a false value. So when we evaluate this logical AND operation, this value is false, and therefore we will short circuit the entire Boolean expression to a value of false. And we did not execute the second operand. So this is some expression and we didn't execute it. Now, actually, in this situation, that's very important. Because notice what was in that other expression. We said sum divided by number is greater than 5. If we divide sum by number and number is equal to 0, that's going to generate a runtime error. So in this situation, the code is actually written in such a way that it is depending on short circuit evaluation to prevent runtime errors. And this is a way to go about that. So by checking to see if the number is not equal to 0 before we check to see if the sum divided by the number is greater than 5, we prevent a divide by 0 error. Because if the number is equal to 0, this will be false, and the second expression in the logical AND operation will never be evaluated. So it's important to understand how these logical AND operations are going to execute. Otherwise, there could be situations where you wind up with odd functionality and odd results that you don't know why they're occurring. Or you see someone's code and you see that they are dividing by a number that they have set equal to 0, and it doesn't cause a runtime error. And you may wonder, why doesn't it cause a runtime error? In this situation, it's because of short circuit evaluation. When the runtime evaluates an expression to false in a logical AND operation, none of the other operands involved in the logical AND operation will be evaluated, and they will be short-circuited to false. Because we know that regardless of what they evaluate to, we are going to wind up with a false value for this entire Boolean operation. So there are rare instances when we want to evaluate the entire condition. We don't want to have a short circuit evaluation. We don't want it to evaluate until it hits a false and then move on. If that's the case, and usually if that's the case, we are wanting to perform bitwise operations, in which case we can use the bitwise and bitwise or to avoid short circuit operation, because bitwise and bitwise or do not use lazy evaluation, which is formally called short circuit evaluation. They will evaluate each operand, even if one evaluates to false. Or in the case of logical or would be short circuited by one of the operands being evaluated to true. Bitwise or does not short circuit in the case of a operand evaluating to true. So let's look at a mini exercise. At this point, pause the video and attempt to figure out which of these Boolean expressions will short circuit based on the left side operand. Okay, in the first expression, the year value is 2015 and the month is 3. So 2015 is greater than 2000. That will evaluate to true. So logical AND does not short circuit in the presence of a true value. It only short circuits in the presence of any operand that evaluates to false. So therefore, this will not short circuit. So again, year is greater than 2015 is greater than 2000. So our year is 2015 and that is greater than 2000. So this expression will evaluate to true. But in this situation, we are performing a logical OR operation. So logical OR is short-circuited by the presence of any expression that evaluates to true. So we have an expression that evaluates to true, and therefore we will short-circuit the rest of the operands. These won't be executed, and we short-circuit this expression to a value of true. Okay, I think hopefully we're starting to get the pattern. So now our year is still 2015. However, we are checking now to see if year is less than 2000. So this expression will evaluate to false, but in this situation we are doing a logical OR test, and OR is not short-circuited by false. OR is short-circuited by true. So therefore, this will not short-circuit. We will have to evaluate whether or not month is less than 4. And finally, we have year is less than 2000, which evaluates to false because year is 2015. And we are performing a logical AND operation. Logical AND in the presence of any operand which is false will always evaluate to a false value. So if either of these evaluated to false, then the entire result of the logical AND will be false, as we discussed previously. So on the left side operand, it evaluated to false. Therefore, we don't even bother executing the right side operand. We don't care. It's not going to have an effect. The value is going to be false. So we short circuit it, do not evaluate whether or not the month is greater than 1, and we move on. So in Boolean algebra, there's something referred to as De Morgan's law or De Morgan's theorem, which is a relationship between the logical AND the logical OR operators. De Morgan's theorem is generally useful to be able to transform between logical AND logical OR operations in various situations. However, specifically in this class, the reason we're introducing it is because there are times when we would like to negate a Boolean expression, and De Morgan's theorem is a way to methodically and accurately negate the entire expression. So consider the situation where we negate this expression. So we're going to put the whole expression in parentheses and throw a not in front of it. So not A and B. De Morgan's theorem says that in the situation where we have not the quantity A and B, we can distribute the not. So not A, not B. So we've distributed the not instead of having it not the quantity. And instead, when we do this, we have to change from an and to an or. And this is De Morgan's law. So these two are precisely equivalent. Not the quantity A and B is precisely equal to not A or not B. So when we have the quantity A and B and we apply the not operator to it, we can apply De Morgan's law and distribute the not so that it applies to the individual expressions A and B, and we change from a logical AND operation to a logical OR operation. So quickly I'll work through the analogous situation where we apply not to the quantity A or B. So now in the bottom row, not A or B, so not the quantity A or B, is precisely equal to not A and not B. This is De Morgan's law. Now to make use of De Morgan's law, imagine we have the code in the bottom left where we are testing in the first Boolean expression if x is equal to 7, and we're combining that using a logical AND with a test to see if y is greater than 3. But we decide that we want to completely negate this entire test. So what we really want to do is apply a not to the entire expression. An easy way to do that using De Morgan's theorem is to negate the logical operation in both of the expressions. So x is not equal to 7 and y is less than or equal to 3 instead of y is greater than 3, and flip the logical operator. So and becomes or, greater than becomes less than or equal to, and is equal becomes is not equal. So let's work through a few more applications of De Morgan's law to negate the Boolean expression in an if statement. So on the left we have a test for x greater than or equal to 0, logical and x is less than or equal to 10. So we need to change three things: the operator for the left test, the conjunction, and the operator for the right test. We will change the conjunction first. And becomes or. Greater than or equal to becomes less than. And less than or equal to becomes greater than. You should be getting the pattern now. In the bottom, if A is less than 10 or B is less than 10, we were going to do some set of statements. So to negate this entire Boolean expression in this if statement, we will flip the less than to a greater than or equal to. We will flip the or to an and we will flip the less than to a greater than or equal to. Let's work through an example program now, which will take in a user's height and weight and produce their BMI. Based on the user's calculated BMI, the program will print out what weight class this person belongs to. So in the bottom left, we see an example run. It prints out an introduction, which tells what is going to occur in the program. It prompts for user information, the height, and then the user typed in 73.5, the weight, user typed in 230 pounds. The program calculated and displayed the BMI, which was 29.93, and then the person was classified as overweight based on their BMI and the table in the upper right-hand corner. Then an additional person went through the exact same process using height 71, weight 220.5. This person has a BMI of 30.75, and that puts them in the range of obese. So let's take a first shot at this. We can put everything into our main function, and we print out first the introduction saying this program reads blah 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 as the first line, which was shown in the previous slide. Then we need to initialize a scanner object so that we can get input from the user. And we print out enter next person's information. We prompt for the height, prompt for the weight. Then we do the body mass index calculation based on the height and weight which the user supplied. And then we are going to print out the BMI followed by the weight classification. So this main will work for exactly one person, and it will do exactly what was done in the previous slide. However, this is a bad solution for multiple reasons. Number one, it's not commented well. So though it's readable because the variable names are somewhat helpful, BMI, weight, height, that helps. There's no commenting to really describe what is going on inside the program and how it's accomplishing it. For instance, we have the BMI formula here, but the way that this is coded is a little bit odd. Weight times 703 divided by height. So it's weight divided by height squared times 703. But this works, but just seems it's a bit of an odd format. Yeah, in general, this is not a good solution, because if we wanted to allow another person to have their BMI calculated, we would have to copy and paste the code. This isn't reusable. It's going to create redundancy, and that's the enemy of good code. One thing to note here is they're using a system.out printf statement. So this is something we haven't mentioned and dealt with very much so far. In a printf statement, we're able to declare a placeholder which we will fill using a comma followed by the variable which we wish to fill into the string. The percent sign acts as a placeholder. This is where the variable's value will be printed into the string. The dot signifies that the next thing which is supplied is the precision. So .2 means we're going to use 2 decimal places of precision, and the F means that we are going to supply a floating point number. So BMI is a floating point number. So rather than being so redundant and having to copy and paste the code in order to have multiple people be able to use it, obviously this is redundant and sloppy coding. Think about it. Could we use methods to do this? Seems like it, because that's what we've done in the past. So methods would certainly eliminate redundancy, and it should simplify the program so that it's more maintainable in the future by others. So how would we go about decomposing this? What methods should we form to accomplish the individual tasks involved in this program? So with any task, there will most likely be multiple ways to decompose the problem, and this sort of leads to a many paths up the mountain situation. However, some of those paths will lead to an acceptable, good quality program design. Others will not. So here's one possible solution. We could write a program which will create a scanner object. Then we'll call a method called person, and this person method will get the height of a person. And this person method will then call a getWeight method, which will get the user's weight, which will then call a computeBMI method, which will then compute the BMI and print out the appropriate information. And then the program pointer will jump back and terminate in their main method. I like the idea that probably spawned this code, because this idea that we're going to treat a person like a software object, and a person has a weight, a person has a height, so we need to get those attributes of that person. That seems in general a decent structure. However, the execution isn't so good. See, we call this method person, which is poorly named because we're not actually forming all of the attributes of a person in this method. We further call a getWeight method. So even though the decomposition looks okay, consider how they went about doing it. These actually string together in sequential order. The main method calls the person, calls the getWeight, calls the computeBMI. So none of these are able to be used without all of them being used, right? When we call person, we have to have getWeight and computeBMI, because person relies on those two as well. So even though this involves methods, it's sequential and it doesn't resolve the issue of readability at all. So as we said, when they decomposed the problem, they may have had a good idea, but their execution of the decomposition was poor because none of the methods are standalone. So this chaining of methods is considered poor style, and usually arises when someone doesn't quite understand how to use methods to decompose a problem into its elemental pieces, into the standalone pieces. So if you notice, you can kind of visualize chaining like this. We called main, then we called person, then we called getWeight, and then we were calling, calculate BMI, then we were going to have to display it. So this is why we describe this solution as chaining methods together. So if we return to this chained method, it should be apparent as you read the main method. We see it come to a method call, another method call, another method call, and another method call. So we just keep going further and further with each method doing a little more of the program, but without each method doing a distinct and separate portion of the program. A good main method should read like a concise summary of the program. So, for instance, this main should read get weight, get height, calculate BMI, display BMI. The reason this is typically better is because each method then is doing one thing and returning a value to the caller, which would be the main. This value can then be passed to other methods if it's necessary, but then the main is sort of directing traffic. And that's what you want. When someone opens a program and begins to evaluate, they should be able to go to the main and read and understand what the program does at a high level. Typically, a program that is built this way, with the main being the center of the program, which calls the individual methods, and each individual method returning a value to the main to be passed as necessary to other methods, yields code which is more reusable and less redundant, because each of the individual methods tends to act on its own without additional dependency. Here's a list of guidelines to be able to help you make better program decompositions. A method should be designed so that it has a clear set of responsibilities. This means that if you design a method to get the user's weight, it shouldn't do something extraneous like call, get, or calculate BMI, because that's not in the set of responsibilities defined. The responsibility of get weight is to get the user's weight and return it to the call statement. So in this way, having clear expectations and responsibilities for each of the methods is going to mitigate this sort of chaining that occurs when the responsibilities become gray and the scope creeps. That's something that we refer to as scope creep. So if a method seems to keep growing and it seems to keep taking on new functions and new operations and performing more and more of the program, that would be scope creep. So decide what the scope is for a given method and constrain it to those responsibilities in that scope. No method should do too large or too small of a share of this overall task. This is similar to scope creep when you have decided what the proper responsibilities are for a given method. That set of responsibilities should not be too large. You don't want to have the main call a single method and that method do everything in the program and then return, and that be the end of your main. Again, this is still not readable code, and it's really functionally no different from putting all the code in the main itself. So if you begin to put too much of the load into a single method, that method begins to be less and less reusable. So define the responsibilities, make sure that it's an appropriately small responsibilities. It's helpful to think of an atomic method, a method which performs one task and that's it. That's atomic because it can't be broken down any farther. And if you add anything else, then you're starting to go beyond one single task. You're starting to combine tasks. So try to program in an atomic way where your methods each are performing a single task, not too much or too little of the program. Minimize coupling and dependencies between the methods, because this will lead to chaining. So it's okay if one method calls another, because, I'll give an example. If when we were drawing the shapes in a few lectures back, our draw egg called the draw egg top and draw egg bottom. Well, that makes sense, and there was a reason for that, because draw egg should have a dependency on draw egg top, and that reduced the redundancy of the program. However, as you begin to couple these methods and have them unnecessarily related, this is going to cause unnecessary dependencies, which will make the code more cumbersome. So the main method should read like a concise summary of the overall set of tasks. Yeah, that's what we've talked about previously. So as you read through a main, if all of the methods are themselves individual tasks and the main is calling these tasks, then the main should read like a summary of the program. So get weight, get height, compute the BMI, and print the body weight classification. That should be how the main method reads, and that would also be a summary of what the program does. Data should be declared used at the lowest level possible, no global variables. So what we're saying here is you shouldn't declare a variable in the main method and make it global and then use this variable throughout all of the other methods that are also included in the class. The reason is this still causes the individual methods to be dependent on information stored in another method. You want each of your methods to be self-contained, individual, functional pieces of the program. And that doesn't happen if you store the memory they need in another method. So don't use global variables. Declare your variables at the lowest possible level. So here is a better solution for how to approach this problem. First of all, we're going to keep some of the elements that we've seen previously. But one, we're going to introduce a method called introduction, which just prints out the welcome method, the welcome statement, and says what we're going to do. Then we declare our scanner, because we always declare the scanner in the main method. Otherwise, that will cause problems for some compilers if we have multiple scanners declared looking at the input stream. Specifically, that'll cause a problem in the Zybooks compiler. So don't declare multiple scanners. We've talked about this before. Rather, declare a scanner at the main method and then pass it into any of the methods other than the main, which we'll need to get information from users. So we've declared our scanner called console, and we pass that scanner to a method called person. This method called person is going to return a double value, which we will store in BMI1. So let's look at this method called person. So we have the method declared public static. It's going to return a double value. So our method heading makes sense so far. We've named the method person, and it's going to accept a scanner object called console as an argument. It'll print enter next person's information, followed by carriage return because we used a print line statement. Then it'll print height in inches, question mark. This won't be followed by carriage return because it's just a print statement. So the user will type in some number, and the console object will return that number as a double because we're using the next double method, and we will assign the value which that method returns to the variable height. Then we'll get weight in a similar fashion. Then we are going to print a new line so that we have an empty line, and we return the result of calculating the BMI. Now understand this return statement. Look at it. So we've got return and then the expression that we intend to return the value of. So when this expression evaluates, we'll have a value, and that's what we'll return. But this expression is actually a call to another method called BMI. So let's look at this BMI method. The BMI method accepts two doubles as parameters and returns a double value. So it accepts height and weight, and it's going to calculate the BMI and return the BMI as a double value. Now notice this method only contains one statement. If you think about it, we could have actually put this statement inside our person method right here where we have our return statement in person. However, this is more readable. Now we can calculate BMI given only a height and weight, and it makes more sense that we would have a method to calculate the BMI rather than coding an arbitrary formula into this method we now call person. So now our person method gets the height and weight for an individual and calculates their BMI and returns the BMI to the main method. So you can't see all of the code in the main, but you can see that we are getting the BMI for the first person and then getting the BMI for the second person, and then we are going to use a method called report to display the results to the console. And this is the report method. So we take in the number, so person 1 and person 2, and their BMI, and print the results to the console. So we will print the string person, and then the percent sign is a placeholder. So we have comma and then number, which was passed in. So in this case, person 1 or person 2. And after the percent sign, we have a D, which means this is going to be an integer value. Then we have colon, which will print as a colon. BMI equals, and percent is another placeholder. Then period signals that we are going to give the precision we wish to have. So we're going to use 2 decimal places. And then F means that we're using a floating point number. So this printf statement will put the number into the placeholder location of this string and the BMI into this placeholder location of the string and print that to the console. Then we have a decision statement to decide how to classify this individual as underweight, normal, overweight, or obese based on their BMI. So now notice the resulting overall program structure and decomposition. We have a main method that prints out an introduction. It gets information for a person. In order to get that information for a person, the calculate BMI function or calculate BMI method is going to be used. And then we have a report that is generated. So from the main method alone, we can read and understand that we're going to print an introduction, get some information for a person, and then print out a report regarding their BMI. And this is a summary of the program. We have very little redundancy because each of the methods performs an atomic task. Print the introduction, get the height and weight, calculate the BMI. So get all the information for the person when these two are combined, and then print the report. So overall, our final solution is significantly better than the previous two.